Okay, we're starting a new chapter now, and we're going to use all those different techniques we've learned for differentiating different types of functions, and we're going to start putting some of those techniques to work to figure out things about different functions. And we've actually talked a little bit about this already, the increase and decrease anyways, and we haven't talked about concavity, but that's what we're going to talk about now in section 4.1. So we'll start off with a theorem. And our theorem says that let f be a function that is continuous on a closed interval, ab, and differentiable on the open interval from a to b. So in other words, it might not be differentiable at the endpoints, but over all the other points in the interval it will be differentiable. And there's three parts to it. So the first part says if f prime of x is greater than 0, right? So if the first derivative is greater than 0 for every value of x in the interval, open interval ab, then f is increasing on the closed interval from a to b, right? So we saw this last chapter when we were talking about monotone increasing and monotone decreasing. The first derivative tells us what the slope of the tangent line is. It tells us what the instantaneous rate of change is. And if that instantaneous rate of change is always positive, it means your function is increasing, right? So our first derivative is telling us the rate of change, and from that we can deduce whether the function is increasing, or as the next point points out, whether it's decreasing, right? So conversely, if f prime of x is less than 0 for every value of x in the open interval from a to b, then f is decreasing on the closed interval from a to b, right? So if it's always negative, right, if the first derivative is always negative in that interval, right, it means that the rate of change is always negative. It means that your function must be decreasing, right? You must have a negative slope basically for the tangent lines at every point on that interval. And the last one, if f prime is equal to 0, f prime of x is equal to 0 for every value of x in the interval from a to b, then f is a constant over that closed interval from a to b, right? And we know that the derivative of a constant is 0. So if you get 0 as a derivative, you know that it's from a constant. Okay, so how are we going to use that to figure out whether a function is increasing or decreasing? And so let's start with a pretty simple cubic function, right? If you graph this, you might want to do that, just plug it into your calculator and graph it. You know what a cubic function looks like, and you'll see where it's increasing and where it's decreasing. So let's see if we can sort of verify that, what we're seeing visually on the graph, with our calculus here for this. So we're going to take the first derivative first. Okay, so we're going to say f prime of x is going to be equal to 3x squared minus 3. Okay. So to figure out where it's increasing, so if we're going to figure out where it's increasing, we're basically solving this inequality. We're trying to solve 3x squared minus 3 is greater than 0, right? So if the first derivative is positive, we know that the function is going to be increasing. To figure out where it's decreasing, we need to solve this inequality, right? 3x squared minus 3 is less than 0. So if that first derivative is less than 0, then it'll be decreasing. Okay, so the way we're going to solve this make a sign chart. Okay, so let's go to the next slide for that. So our derivative was 3x squared minus 3. And we're trying to figure out where it's increasing, right? Where it's greater than 0 and where it's less than 0. So the first thing we're going to do is set this to 0. So 3x squared minus 3 equals 0. I'm going to solve this by factoring, so we get 3 times x squared minus 1 is equal to 0, and that's just the difference of squares. I'm going to factor that into x plus 1 times x minus 1. That's equal to 0. And then set each factor equal to 0, so from this factor we're going to get x is equal to negative 1. And from this factor we're going to get x is equal to positive 1. Okay, so let's make a sign chart. So these are the points where your function is equal to 0, right? So it's equal to 0. So let's do sine of the first derivative. So the sine of the first derivative, we're going to just pick some test points. You remember doing this from pre-calculus. So we're going to pick some test points. Let's say there's basically 3 intervals we need to test. We need to test this interval from negative infinity to negative 1. We need to test this interval from negative 1 to 1. And we need to test this interval from 1 to positive infinity. So we need a test point in each of those 3 intervals, right? The sine of the first derivative is 0 at those 2 points. So pick our test point. So I'm going to pick a test point, negative 2, for this interval, right? So this interval is from negative infinity to negative 1. And then between negative 1 and 1, we're going to pick another test point. So let's pick 0. That's nice and easy. And then for 1 to infinity, that's our third interval, from 1 to positive infinity. We need a test point, and I'm just going to pick 2. Doesn't matter what point you pick. Obviously, you want to pick something that's going to make it worthwhile. And so just test these. So what's the first derivative, right? We're going to evaluate the sign of the derivative, right? Not the sign in the function, but the derivative. So what's our derivative evaluated at negative 2? So negative 2 squared is 4, right? 3 times 4 is 12, minus 3 is 9, right? So that means for this entire interval, f prime of x is going to be positive, right? So our conclusion for that, right, we can conclude from that f of x is increasing on this interval from negative infinity to negative 1. And I'm going to do a closed interval for that. Okay, so we want to do this again. We want to evaluate it at our other test point. So for our other test point is 0, so we need to evaluate the derivative at 0. So we get 0 squared is 0 times 3 is 0 minus 3 is negative 3, right? So let's switch the color a little bit for this. Let's do purple maybe. So our function, right? Since our derivative is negative in that interval, our function is decreasing. So f of x is decreasing on the interval from -1 to 1. So it's the closed interval for increasing or decreasing. You're including the endpoints. And then finally, right, we test that last point there, right? I'm going to test the derivative at 2, and we're going to end up with 9 again for that. So that's positive. So over that entire interval, the first derivative is positive, right? So the conclusion we're going to make for that is f of x is increasing. I'm running out of room like I usually do. So increasing on 1 to infinity. Okay, so graph that on your calculator, and this is basically what should be happening. You should have a graph that's increasing from negative infinity to -1. I should have plotted some points for this. So anyways, it should be increasing. I'm not going to plot points. I'm just going to show the shape of it, right? It should be increasing to -1, decreasing to +1, and then increasing again, right? Just what you'd expect from a cubic function, right? That's the shape you expect from a cubic function. Okay, so the first derivative, like we've been saying all along, is telling us what our rate of change is, right? And so if we get a positive rate of change over an entire interval, then the function is increasing over that interval. If we have a negative rate of change over an entire interval, then our function is decreasing over that interval. Okay. So, like I said, we saw a little bit of that when we talked about monotone increasing and decreasing when we're talking about one-to-one functions. How do you see it? Tell whether a function is one-to-one or not. That was one way that we could see it. Okay.